Well, I will get started. Dearly Father, we thank you for the break, time to relax and refresh. Help us to just get back in the swing of things today. Just pray that you'd be with students, help them ask good questions as they have them, and I just pray that we'd all learn more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. So you guys have any questions? Yep.
Can you work through
the Minkowski, the last problem? So I think roughly speaking, the last problem is to study, you guys will have to help me out here. What were our equations? What was it? It was T prime, what was it, gamma, X prime, gamma. Now I remember the X was X minus VT. This much I remember. I think the T is T minus Vx over C squared. Is this right? So these are the Lorentz transformations, right? If I'm wrong about these, it's important you tell me now before I waste like a board of algebra on a fool's errand, right? So now I think this gets cleaner if you look at it as CT prime. CT prime is gamma times CT minus beta x, I believe. And here I'm introducing the beta as V over C, right? So like V over C is beta, so if I basically multiply this equation, multiply by C, that gets me to here, right? Yep.
I think it's x prime is equal to gamma times x minus V over C times C.
That feels wrong. Let's see here. Let's see here. According to Wikipedia, so it must be right, right? I mean, what's on Wikipedia is the result of years of nerd battle. It's a higher form than like editing in an encyclopedia. You guys know what an encyclopedia is? Before there was the internet, we used to have these things called books. And then people would compile the knowledge of gatekeeping experts into these books we called encyclopedias. And then we would all reference it as if it's some sort of like sacred form of information. And then English professors would criticize you for using information on the internet rather than in these encyclopedias if you were me and your age. Which is kind of funny because I think actually, well anyway, any medium has its faults, right? But yeah, T minus Vx over C squared. Yeah. All right, so that's right. Now, of course, on the other hand, y prime is y and z prime is z, right? And I think, if I'm remembering the last problem correctly, annoyingly I left it in my office for my convenience. I asked you to look at the interval between events, right? I had like event 1 and event 2. You'll have to remind me the notation, Sam. I don't remember the notation. I'll just make up a notation. It won't be helpful to you if I do that, but.
I think it was G of vector, 4 vector V, 4 vector W.
Ah. So like this. Oh, sub O's. Oh, sorry. Sorry, my superscripts are showing. I'll fix it. All right. And I may have used a different notation. Did I use like an angle bracket or something? Or? Okay, cool. And so I was saying to look at V, I want to say it was like, on the one hand, oh, goodness gracious. Let me not try to remember my silly problem off the top of my head. I do have it posted. Oh man, I had it open, I just closed it. That was dumb. All right, let's try this again. So I had taking the difference between events. So I want, on the one hand, V bar to be E2 minus E1 versus V bar equal to E2 prime minus E1 prime. Maybe I should say, I don't know, I'm not sure my notation is great here. Well, I avoided this by just talking about directly. My bad. So, well, I could say basically I'm looking at this versus this, and I want to calculate this in both cases, right? And my intention was to show that those are equal. All right, so the question is, what is this event I'm talking about? Well, like E1 would be CT, 1, X1, Y1, Z1, right? E2 would be CT2, X2, Y2, Z2, right? So one of the things we should notice that will greatly simplify our life is that if we write this, notice that, let me just try to do it over here. So if we have CT2 prime is equal to gamma times CT2 minus beta x2, right? And if I have CT1 prime, I have gamma CT1 minus beta x1, right? If I take the difference of these two equations, what does it give me? I get C delta t prime is equal to gamma times C delta t minus beta delta x. I have a suspicion this is very helpful to us in this problem. Noticing that the Lorentz transformation equally well holds for the difference between events, right? So like, when I think about, you know, E2, let's say E2 prime minus E1 prime, what is that? Well, that's actually equal to C delta t prime, comma delta x prime, comma delta y prime, comma delta z prime, where I'm defining delta t prime to be what? Like t2 prime minus t1 prime, etc., right? What's delta x prime? Like x2 prime minus x1 prime, and so forth. Are you guys with me? I haven't really calculated anything yet. I'm just throwing labels on the board. So I would like to show that the Minkowski product of this, you know, E2 prime minus E1 prime is the same as the Minkowski product of E2 minus E1. And that's actually going to be pretty easy here if we use this delta notation. And so let's try it out. So G of E2 prime minus E1 prime, in other words, is equal to what? So let me just make some labels here, right? So this is my V0, this is my V1, this is my V2, this is my V3, right? So we've got what? We've got minus V0, and my bad, I did it, good grief. You have to enter a pair into this thing, so All right, so I'm supposed to do minus, according to the definition in the problem, minus V0 W0 plus V1. But V and W are equal here, right? So minus V0 squared plus V1 squared plus V2 squared plus V3 squared. All right? So what is that? Well, V0 is C delta T prime squared, right? So I've got minus C squared delta T prime squared plus delta X prime squared plus delta Y prime squared plus delta Z prime squared. Now, delta Y prime and delta, look at this. This is, what does this say here? Do you guys see what this says? This means that the change in Y prime is equal to the change in Y, right? I mean, and this one gives us that delta Z prime is delta Z as well, right? Like Z2 prime minus Z1 prime is equal to Z2 minus Z1 and vice versa for Y. So these two, there's nothing to do there really, right? They just ride along. The first two is where the fun stuff happens. So I've got minus C squared. Now delta T prime is what? It is, put parentheses here, gamma times what? Times delta T. Oh man, I would do better to not keep that C outside, wouldn't I? I would do better to put the C with the delta. I should keep the C. I'm just going to take the minus outside and keep the C with me. See, because I've got a nice formula. I've got a nice formula for C delta T prime quantity squared, right? And delta X prime. Not really doing much in this step at the moment, guys. I'm going to, finish these ones over here, right? And then what? So C delta T prime, remember, we worked out over here, it's gamma times C delta T, right? Gamma times C delta T minus beta delta X. Did I remember it right? And then over here, I've got gamma times delta X minus, golly, what was it? Oh, I guess I hadn't worked that out yet, had I? What's delta X prime equal to? So basically the same algebra works that out, right? So delta X prime is gamma times delta X minus V times delta T. By essentially the same algebra I went through for the delta T prime. So delta X minus V delta T. Now I got to square this thing, right? And you still got your delta Y squared and your delta Z squared over here. So how does this all go? So it looks to me like I've got a gamma squared both places, right? So I've got like minus gamma squared times what? Times C squared delta T squared minus 2C beta delta X delta T plus beta squared delta X squared. That's the first term, right? And then the second term, I've got plus what? Plus gamma squared delta X squared minus 2 delta X V delta T plus V squared delta T squared. close the parentheses, and you still got your delta y squared plus delta z squared, which I'm starting to get tired of writing. Maybe I should give that a name. Now, what's the situation here? Anybody see anything pop out at you, algebra-wise?
Beta could be replaced.
Ah, so C beta is actually what? Is V, right? What does that say about the middle terms? Look at them. You've got a delta x delta t, 2c beta. That's really 2v delta x delta t, which is what I have over here. 2 delta x delta v times v. These are the same. Notice the net minus out here. That means so the future's looking brighter, right? Because now we can group like terms. See these guys? One here and one here. Where do those go together to give you? I'll keep the c squared out front. So c delta t squared times what? Maybe I should keep a minus in front of that. I'll keep a minus. Minus c delta t squared, and then that's times gamma squared from this one. How about the other one? Oh, look, I don't have a c over here. So if I'm factoring a c squared out, I divide by c squared, right? So that means that I have to say minus beta squared times gamma squared. Here, beta squared is v squared over c squared. A little tricky, but do you guys follow me? So I factored this c delta t squared out. Part of this is because I know what I'm going to. I'm trying to find my way back to the Minkowski metric, but for without the primes. And without the primes, I'm looking for a minus c squared delta t squared. So I want this, but without the prime as my end result. So that's why I factored that out. Now I've got a gamma squared from the first one. But this other one over here, I've got v squared, right? So that v squared I convert to beta squared over c squared times beta squared. See, v squared is equal to c squared beta squared. So I took the one c squared and I factored it out to that, and I took the other beta and I left it here. That's how I factored this term. All right, then next, I have plus delta x squared. And what do I got? Well, looks like I've got a minus gamma squared beta squared from the first term. And how about over here? Well, this was easier, plus gamma squared, yeah? And then, of course, I still got the pesky delta y squared plus delta z squared. But what was gamma equal to again? Do you guys remember? Remember, gamma was equal to 1 over the square root of 1 minus v squared over c squared, which is equal to 1 over the square root of 1 minus beta squared. So what that means, among other things, is that gamma squared is equal to 1 over 1 minus beta squared. Which also means what? That means that 1 minus beta squared is equal to 1 over gamma squared. I think this little bit of algebra right here is especially relevant to us. See, because I can factor gamma squared out of both of these, right? See that? I've got gamma squared times 1 minus beta squared. I mean, however you want to do the algebra here, there's a lot of different ways to do it. But however you do it, you should see that what we're getting just simplifies to 1, right? So what we got is minus c delta t squared plus delta x squared plus delta y squared plus delta z squared, which, by the way, would be equal to g of E2 minus E1, comma, E2 minus E1, which is what you're asked to show in that problem. Sorry if I took too much of the mystery out of it. Ah! Yowzers! So this quantity that I've calculated is called the invariant interval. So if you have two events, you can compare the invariant interval between two events in any two different frames of inertial frames of reference, and you'll have the same invariant interval. So like if this is positive with respect to one frame, it'll be positive with respect to any other frame. If it's 0 with respect to one frame, it'll be 0 with respect to any other frame. If it's negative with respect to one inertial frame of reference, it'll be negative with respect to any other inertial frame of reference. And this is how physicists classify events. If you have two events, you can classify whether they're, either time-like separated or space-like separated or light-like separated. And so, the most perhaps famous version of this is if you think about the origin as one of your events, then you can think about the light cone like this. All right, and here I'm graphing x and ct like that. And so if you let me erase this figure. Sorry, the span of the board. E1. I say it out of love. My calculus teaching would be far less malevolent if not for Dr. Sprano being here. So I was very easygoing. I didn't do proofs or anything before Dr. Sprano came. Like he came, I was like, oh man, I got to prove things. So I just completely changed my way of calculus teaching. That's only partly an exaggeration, but anyway. So E2, say CT X, Y, Z. So like if E2 is here, then that would mean that it's time-like separated from the origin. In other words, you could reach it. It's causally connected. Like you could travel a world line less than the speed of light to get from the origin to E2. If you work out the invariant interval, well, I don't know. I have the thing I forget, guys, is which one's positive, which one's negative. See, it's annoying. Some books put minus, plus, plus, plus like this. There's equally many books that put plus, minus, minus, minus. And it turns the meaning of plus and minus upside down. But in any event, so the ones up here are time-like. So like time-like. And time-like's also down here. Out here, you've got space-like. And over here, you've got space-like as well. The events which have a space-like separation from the origin, these you cannot access without using faster than speed of light travel. And then, of course, the light cone, these are the events that you can reach from the origin by sending a light ray. And we just draw a two-dimensional version of this, but technically it's four-dimensional space. So if you added another dimension, it's honestly a cone, right? But anyway, this really doesn't have anything particularly to do with that homework question, but I think it's part of a larger discussion that's worth having. Do you guys have other questions? I hope that helps. I don't think I would ask this one on the test, right? I just wanted you to appreciate how this all algebra kind of works through. It starts to give you a sense of how these things are done. If you keep studying this course, you use this to solve problems, all right? Like there's tons and tons of problems that you can solve with this algebraic observation. Yep. Yes, sir? The test is Friday, that is true. And the test is predominantly not special relativity, right? The test is predominantly what? Energy conservation, momentum conservation, right? With a hint of special relativity. So there's probably 10% special relativity on the test, maybe 20% on the outside, right? More likely 40% momentum, 40% energy, something like that. More than likely. So, does that make sense? Well, I don't know if it makes sense or not, but it's what we're doing. Oh, I'm almost forgetting. I have things to share with you guys. Let's see here. Let's see, where should I start? I have to start at the beginning. All right. Let's see here. Is that the first? It's the second. This is a recent thing for me. I've been on this mailing list. So I was going to try to work these into lecture here. See if I can find the first one. Oh, okay, here we'll start with this. What does a polar bear like to eat? No. The answer is a burger. Like like it's cold. Next question. Where do animals get all their groceries?
Food line.
The food lion, thank you. I think your mind is going where it needs to. Let's see here. Next question. Where do tornadoes like to eat? Dr. Sprano's answer was trailer parks. It's kind of darker, but the correct answer would be Wendy's. Wendy's. Let's see here. What else do I have? Now, don't get. I'm not always going to have so many of these. This is because I have like 2 weeks of these built up. What do you call a sea creature that studies space? Confused. The answer is a starfish. This one's kind of abstract, so, all right. What toy helps your knees? Very good. Answer is Legos. Leg-O's. I told you it's kind of abstract. Oh, and the other one was, where do you get money? The Dollar General. Now, my wife said no, the Dollar Tree, because that's where money grows. And then the source of these jokes agreed that that was funnier. So, these are from my nephew. He's about 10. He said I heard he has this mailing list. If you give him his email, he'll send you one every day. And I was like, I want, please send me these. So I said it will greatly improve my teaching, so.
You're going to get one every day?
You're welcome. I care about the pedagogy and then do my part. What's that? He doesn't really give me one every day though. Like I was hopeful. Now my son has been inspired to start his own, but my son is like 6. So you have a hope of making sense of the jokes I just told you. The jokes that my son will come up with, the 6-year-old, they're not going to make any sense. They're going to be like totally like an elephant sat on a park bench. What was that? Is that the joke? Yeah, that's the joke. Like, oh, funny. Stuff like that. All right. Other questions? Did you guys see the video I posted over break? I actually did solve a couple problems in there with numbers at the end of it. They should be helpful to you, right? I was going to say the other thing I should mention is, just to finish the discussion about relativity a little bit. The special relativity was discovered by Einstein, 1905 or so, right? And so just to finish the history discussion I started in here. I guess I'll do over here. So it's special relativity, 1905, right? And so that same time period, Einstein also published a paper on the photoelectric effect, which turned out to be right on the money. And he also published, you guys know in chemistry, Avogadro's number? 6.023 times 10 to the 23rd or something like that, I forget. But ever ask a chemist why that's the number of molecules? Ask them, see if they know. I bet they can't explain it to you. I have some empirical evidence on this because every chemist I've ever asked to explain it to me hasn't been able to. And the reason for that is it's a technical result that comes from studying Brownian motion. That was also in a paper that Einstein wrote in about 1905. He calculated Avogadro's number from the statistical physics of molecules. You got to understand, in 1905, not everybody was convinced there was such a thing as a molecule. That was still kind of new thinking, right? There was more of an idea of matter just being sort of this like gelatinous ooze that just kind of was like smoothed out. There's like a continuum of stuff. The idea that there was at the base of things like little particles is an idea that we've only recently really glommed onto. But anyway, so 1905, special relativity, and then general relativity about 1915, right? So general relativity, as I told you guys, it predicts that there will be a redshifting of radiation in gravitational fields. The frequency changes if you emit light at one radius, distance from the center of mass, and you absorb it at another. The frequency changes according to the change in radius. And this adjustment in frequency has to be accounted for to make GPS work, right? So that was the answer to the other homework question, right? But in terms of experimental tests, there were three, right? You had the perihelion of mercury. Do you guys know what that is? Well, I don't think that's quite right, what I've written here. It was the precession of the perihelion of Mercury. It's a mouthful, but what it's talking about is the planets, they go in, oh, goodness gracious. So here's the sun, right? So the orbit of Mercury is something like that, right? But it doesn't stay like that. As it goes around, this egg kind of rotates. All right? Like that. So this motion here, that's the precession. So the precession of the perihelion. And goodness gracious, I forget the exact numbers, but over a century, there's so many arc seconds this goes through. And it turns out that classical mechanics, the general, just Newton's gravity, all right? Newton's gravity was what? We'll talk more about this after test, right? But force of gravity, Newton's universal law of gravitation is this GMM over r squared, basically, right? So that force of gravity, as it interacts between all the different planets and the sun, accounted for most of the precession of the perihelion. And then there's some other complicated, like astronomical thing I don't understand. I'm not an astronomer. But there was like left over this 43 arc seconds per century that couldn't be explained. And also mathematicians got good enough at their calculations that they realized that 43 arc seconds was not, couldn't just be ignored. It couldn't be just chalked up until we miscalculated it. It turns out that when you run through the calculation in general relativity, it produces exactly this 43 arc seconds. So that was the first thing, one of the first things that Einstein calculated was that, to check that general relativity actually would account for the known discrepancy of the precession of the perihelion of Mercury. So that was one thing. The other thing was in 1919, Sir Arthur Eddington, and I don't know if I told you guys this stuff already. If I did already, I'm sorry. The trouble for me is I'm also teaching a student general relativity as an independent study through Zoom. And, well, not exactly. I'm just posting videos for him. So I've been making videos on this stuff. And so I'm sometimes forgetting what I've told you guys versus what I put on the video. Yeah. But Eddington in 1919, he observed light bending around the sun in a total eclipse. And it's debated whether or not he actually did it or not, but that's another possible, like, early experimental. Since then, the way that light bends around massive objects, according to general relativity. This is called gravitational lensing. This has also been observed a number of times. And then, of course, the other thing was just redshift. Okay, so none of this is in any way related to really the history, not too much anyway, related to the history of the cosmos at all, right? But the other thing that happened with general relativity is it started this discussion which led to, well, the Big Bang, right? The whole Big Bang idea. And so to start with, Einstein originally proposed, do you guys know what Einstein proposed originally? He proposed his static universe. Now, why did Einstein propose a static universe? Do you guys know? What's that? Like, why would Einstein? So Einstein, much like many other natural philosophers of his philosophical bent, so the universe always has been. It always will be. It just is, right? And if you believe that, then maybe you don't think you have to explain where it came from, right? So, does that make sense? Yeah. So, but then the trouble was, well, the trouble was that it wasn't too long after. I mean, this is probably 1920 or so. I'm not sure exactly when Einstein proposed the static universe, but that gave way to observations of what's called redshift, right? So what's redshift? Do you guys know? So redshift is, yep. Yeah, it's like a Doppler effect, except this is a Doppler effect that comes from what they think. I only partly believe these things, all right, guys? So, so the light traveling from wherever it came from, as it traveled, the universe has expanded. In the process of the universe expanding, the light has gotten redshifted. And the reason you can tell it's redshifted is, there are things that have a certain sort of spectrographical footprint, right? Like sort of a DNA. You have certain chemical processes. You have relations of different energy bands for chemical processes. There's very specific EEV signatures of certain chemical processes. And so you can look at that and you can see that they've been shifted from what we observe here to something else. Like it's the same, it's kind of like, taking a musical piece and like shifting it up an octave or something, or down an octave perhaps would be the better way to look at it. So, so you're like, I know what that is, but it's at the wrong frequency, right? Because it's been redshifted. And so something like that is how you calculate redshift. So the redshift implies that there's Big Bang, the Big Bang cosmology. And what is that? Well, the Big Bang cosmology, the idea basically is that, well, it was the solution to relativity, general relativity, that sort of you hang your hat on is, well, I mean, there's different ones, but roughly speaking, it's something like the, I would say it's related to the Schwarzschild solution, like the solutions for a black hole. You travel it back in time to time equal to 0. There's a singularity at time equal to 0. From that singularity, the universe expands, right? And it doesn't expand into something. It's space, it's time itself that's expanding. This is the idea, all right? And so in the Big Bang cosmology, a prediction of that is that the light will be redshifted as we've observed, all right? So then what happened? So the redshift, do you guys know when this was observed? Redshift? See, this I'm a little fuzzy on, but I want to say like in the 60s or something, maybe like 61. Honestly, I don't remember. Before I was born, that's for sure. But so the story goes something like then in their creation myth, right? That you have this initial singularity from nothing, the universe just pops into existence, however that works. And then it's a very pressurized, hot, dense soup of things. All right? All of the things that we know and love, like protons, electrons, these things are all destroyed because there's such high energies. We're talking about just pure energy. And as that expands, it cools, right? At some point, you have things like neutrons and protons and the matter that we're familiar with start forming in this story, right? And the problem is that is tied to what's called the cosmic background radiation. So the cosmic background radiation, CMB, I think this was like, oh goodness gracious, I can't remember exactly when this was measured, but the cosmic background radiation was measured at some point. And so that sort of further, you could look at it as evidence that sort of indicates maybe there's something right about the Big Bang cosmology. I mean, I know there's lots of things wrong about it because when I read Genesis, it doesn't line up with the order of events, so I know it's wrong, right? But exactly how it's wrong and why it's wrong, I don't know. Like, it depends on which decade of cosmologists you want to argue with because they change their story every decade. So, like, it's a moving target if you want to disprove these things. But anyway, a lot of the story remains the same. So anyway, the cosmic background radiation sort of freezes into place. Listen to their stories, give or take like 3 minutes, something like this. All right, 3 minutes after the initial singularity. Now, you might wonder, what do I mean by 3 minutes? Because I just got done telling you that time doesn't have an absolute meaning, right? Like, we're rotating time. If I say the difference between one event and another is 10 seconds, you should ask me with respect to what frame, right? Because if you measure me the distance between one event and another with respect to another frame of reference, you might say it's 20 seconds, right? So there's no universal notion of simultaneity in special relativity. How is it we're talking about time in general relativity? Well, the reason is there's this like universal background frame that is co-moving from the initial singularity. So it gives you this like frame of reference that you can reference, right? It's the amount of time that a given point of the universe has experienced since the initial singularity, the so-called co-moving coordinate. And with respect to that co-moving coordinate, after about 3 minutes, things freeze out, right? And that freezes, if you will, the cosmic background radiation. And then it kind of expands out, right? Once things freeze out, that initial radiation from before with the hot energetic soup, it's still sort of stuck in place. Okay, so here's the thing. When you look at the cosmic background radiation, it's so uniform, it would imply, according to the standard Big Bang cosmology, that there are things which are in different parts of the sky that froze at the same time. What this means is that there has to be some sort of like superluminal communication between causally disconnected things. In other words, if you accept the standard story before about 1975, all right, it violated standing ideas about causality, because to say that you saw this like pattern in the sky, it was too big. If you followed it back, it would say that, that pattern to be formed, it had to be formed in such a way that things which were outside each other's light cones were communicating. This cannot be, right? And I don't think, so like the book I was looking at by Sean Carroll is, he talks about CMB as a consequence. So the other book I read before on inflation, it talked about the large scale structure of space and time. And I don't know, I'm not an expert in all this stuff, guys, I just read some. But anyway, so what's the solution? How do you fix this? The fix to it, so the idea had been before that the expansion of the universe was at a uniform rate from the initial expansion, and it just kind of uniformly expanded out. The way to fix this, and this is an experimental contradiction to the initial model, like that there is this large scale structure. The solution is simply this, is that in the initial moment of the universe coming into existence, it goes from nothing to something like e to the 60th of its initial size. In an instant, it goes from something to an incredible expanse. In the process of doing that, that explains how the things which were close together are still related, even though they're really far apart. See, because they got froze in the inflationary process fixes this causality problem I was talking about when you sort through it. Yeah. In a moment? Which one?
You said in a moment the universe became significantly larger.
Right.
What period?
No one ever quite explains exactly the time. I mean, the inflationary model, first of all, that's not accurate, right? So I'm describing, basically people drew a line through this and they replaced it with inflationary cosmology. So what's inflationary cosmology is this idea that after t equals 0, so like the equations break down. I'm not sure that the question entirely makes even sense. Like going from t equal to 0 to t equal 0.1, is that like really a meaningful thing to talk about? I'm not sure. Suppose it is. After like, during the first, let's say 0.1 seconds, something like that, there's this incredible inflation from 0 out to an incredible extent. And then from that point, it slowly, then the inflation slows and it keeps expanding, right? But not at that incredible rate that it did to start with. So they just know it's observationally necessary to assume that the creation of the universe happened in an instant, not over a slow and gradual period of time. That's what the experimental evidence leads us to say. Now, these things are incredibly speculative, right? This inflationary cosmology is not one theory. When I was in grad school, I asked my general relativity professor what he thought of inflationary cosmology, because I just got done reading a book as an undergraduate. And he told me, he said, which one? There are 150 models. That was, 2002, maybe? 2003? I'm guessing there are more models now. It's so the idea roughly though is that there was something called an inflaton field. And that field dumped its energy into the expansion of the universe. And after that field was exhausted, it's no longer expanding. To answer your question, I think that's kind of the idea. Again, I think these things are incredibly speculative. I don't really believe them. I am amused that in the course of a century, we've gone from, I want the universe to exist forever so it doesn't have to explain itself, to, oh, well, it had a beginning, to, oh, it couldn't have had a beginning and then slowly expanded. It had to be created, my word, not theirs, in an instant. I mean, the big picture of things gets closer and closer to what we read about in Genesis in terms of something to nothing, from nothing to something, which I think is very interesting. And yet I know a lot of it's wrong because there's stories of, how the stars and planets came to be. Some of the timeline is wrong in terms of Genesis. And I believe Genesis because the difference between us and God is that God was there. So I think eventually observations will drive us to the Genesis account. I'm just sketching to you what's more or less believed by secular astrophysicists and such, as I understand it. I guess I'm out of time.